useful aspect of regression is that it can divide the variation in y into two parts: the variation in the predicted scores and the variation in the errors of prediction. The variation of y is called the sum of squares y and is defined as the sum of the squared deviations of y from the mean of y. The formulas for the sum of squares y, or SSY, for both the population and a sample are shown here. A simple example is given in this table. The mean of y is 2.06. The second column shows the mean subtracted from each y value. The third column is the square of each value in the second column. SSY is the sum of the values in the third column and is equal to 4.597. It is sometimes convenient to use formulas that use deviation scores rather than raw scores. Deviation scores are simply deviations from the mean. By convention, small letters, rather than capitals, are used for deviation scores. Therefore, a lowercase y indicates the difference between capital Y and the mean of y. This table shows the use of this notation. The numbers are the same as those in the table shown previously. The data in this table are reproduced from the first section of this chapter. The sum of each column is shown in the last row. The column x has the values of the predictor variable, and the column y has the criterion variable. The third column, small y, contains the differences between the column y and the mean of y. The fourth column, small y squared, is the square of the small y column. The fifth column, y prime, contains the predicted values of y. In the introductory section, it was shown that the equation for the regression line for these data is y prime equals 0.425x plus 0.785. The values of y prime were computed using this equation. The sixth column, small y prime, contains deviations of y prime from the mean y prime. The seventh column, small y prime squared, is the square of the small y prime column. The next to last column, y minus y prime, contains the errors of prediction, consisting of the actual scores, y, minus the predicted scores, y prime. The last column contains the squares of these errors of prediction. We are now in position to see how the sum of squares y is partitioned. Recall that the sum of squares y is the sum of the squared deviations from the mean. It is therefore the sum of the small y squared column and is equal to 4.60. SSY can be partitioned into two parts: the sum of squares predicted, SSY prime, and the sum of squares error, SSE. The sum of squares predicted is the sum of the squared deviations of the predicted scores from the mean predicted score. In other words, it is the sum of the small y prime squared column and is equal to 1.81. The sum of squares error is the sum of the squared errors of prediction. It is therefore the sum of the y minus y prime squared column and is equal to 2.79. As shown in the box below the table, the sum of squares y equals the sum of squares predicted, SSY prime, plus the sum of squares error, SSE. And indeed, 1.81 plus 2.79 equals 4.60. There are several other notable features about this table. First, notice that the sum of small y and the sum of small y prime are both 0. This will always be the case because these variables were created by subtracting their respective means from each value. Also, notice that the sum of y minus y prime is 0 when you take rounding error into account. This indicates that although some y's are higher than their respective y primes and some are lower, the mean difference is 0. The sum of squares y is the total variation in y. The sum of squares predicted is the variation that is explained, and the sum of squares error is the variation that is not explained. There is an important relationship between the proportion of variation explained and Pearson's correlation. R squared is the proportion of variation explained. Therefore, if r equals 1, then naturally the proportion of variation explained is 1. If r equals 0, then the proportion explained is 0. Finally, if, for example, the correlation is 0.4, the proportion of variation explained is 0.16. Since the variance is computed by dividing the variation, also called the sum of squares, by n for a population, or n-1 for a sample, the relationships just spelled out in terms of variation also hold for variance. For example, the total variance is equal to the variance of y prime plus the variance of the errors of prediction, y minus y prime. Similarly, r squared is the proportion of variance explained as well as the proportion of variation explained.